All right, so last time we started talking about related rates. So you guys had a few related rates problems for your homework. They do get a little bit more difficult. You saw some pretty difficult ones towards the end of class last time. One problem that I gave you guys on your homework had to do with two sides of a triangle. Do you guys remember that problem? So it says two sides of a triangle have lengths of 12 and 15 meters. The angle between them is increasing at a rate of 2 degrees per minute. How fast is the area of the triangle increasing when the angle between the sides of fixed length is 60 degrees? So this is the exact same problem that was from your homework. But I'm going to teach you something new today. Okay. If something is never changing, do you guys remember how like if the side length of A was never changing, then when you did dA over dt, it was equal to 0, right? Things would cancel out. If something is a constant, we can plug them in. So it says technically it's okay to plug in numbers, but only when they are constant values. So in other words, when like dx over dt or whatever is equal to 0. Okay, so that you can see that in this first example. What it's talking about is if you have a 12 meter, like a stick, and a 15 meter stick, okay, those are fixed lengths. So when you're making it larger, those lengths aren't changing. Okay, so that's what you had on your homework. The theta is the angle between them. You're creating some kind of triangle. Okay, so your area is equal to 1/2 AB sine of theta. All right, stop this. Okay, take the Tootsie Pop out. We're doing a Tootsie Pop lab along with this, so. Okay, so we have A equals 1/2 AB sine of theta, and A and B are both fixed lengths. Okay, so that means we can actually plug numbers in for them now. Most of the time, you cannot do this. Okay, so I went to a conference with a lady, or I went to a conference a few years ago at Butler. It was for a bunch of AP Calc teachers, and I had this lady in there who's like, I never let my students plug in values. I make them take the derivative first. But I do some really hard related rates problems. One of them is a trapezoidal trough, which we're going to do later, and you would cry if you had to take the derivative. I mean, you almost cried on your homework the other day, right, with this, when I made you take the derivative of A, B, and theta. You were like, no, I'm done. All right, so I'm going to go ahead and plug in the number. So I have 1/2 A, B, but theta is something that is changing. So I cannot plug in that 60 degrees here. Because if I did, when I took the derivative, it's just going to be 0, right? That's not interesting. So I have, let's see, 1/2 times 12 times 15, so 90. So 90 sine theta. And I now take the derivative with respect to time. So I get dA over dt equals 90 times cosine of theta times d theta over dt. Wasn't that derivative so much nicer? Man, don't you wish I had taught this to you last night? All right, so now we need to find the rate of change of the area. So how fast is the area increasing when theta is equal to 60 degrees and the angle is increasing at 2 degrees. So I'm going to have 90, I'm going to have cosine of 60 degrees, and I'm going to have times 2 degrees per minute, so times 2. Now you guys should all know 60 degrees, the cosine of 60 degrees, what is it? Don't fail me now. Oh, you can't talk because you have Tootsie Pops in your mouth, right? Or 1/2. All right, take a Tootsie Pop out of your mouth. All right, so we have 1/2, and then we have times 2. So you end up getting 90. Did you guys get that on your homework? That's the answer you should have had on your homework. Now your units, since it was in meters, it's going to be meters squared per minute, right? Area is meters squared, time is minutes. So 90 square meters per minute for the two sides of a triangle one. All right, the next one. So it says a balloon rises at a rate of 3 meters per second from a point on the ground 30 meters from an observer. Okay, so we need to draw a picture. Most of these you will need to draw a picture, right? Okay, so we have...
It's meters squared over what?
Minutes. Okay, so we have 30 meters down here, and a balloon is going up. I don't know what kind of balloon. We'll make it a hot air balloon. That's a lovely balloon. Hopefully Monica and Neil aren't traveling in that hot air balloon. Do you remember that story? All right, do you guys know that? Yeah. Okay, so it rises at a rate of 3 meters per second. So we'll call this y, and dy over dt, it's adding 3 meters every single second. Okay, so find the rate of change of the angle of elevation of the balloon from the observer. We're going to pretend this observer is lying on the ground, actually. They don't have eyes on their toe, like I've just drawn it. All right, so we're going to find theta. We're going to find the rate of change of theta. So basically, we need something that relates 30, theta, and y. So what's an equation that relates those things? Jeez, that was a loud one. All right, so it's about battery round. All right, so I heard Hannah say that it is tangent. She yelled out TOA, so tangent is correct. So it's going to be tangent of theta is equal to opposite over adjacent. Now, you can call that x, and you can do y over x. But in this case, right, 30 is constant. You're not moving like closer to the balloon or anything. So since this is constant, you can plug it in. So you get tangent of theta equals y over 30. And then I'm just going to multiply the 30 over just because I don't want to have to worry about 1 over 30 y. So you can always rearrange as needed before you take the derivative. Okay, so now we take the derivative implicitly. So I'm going to have 30 times derivative of tangent is secant squared, right, times d theta over dt equals 1 times dy over dt. All right, and now we plug everything in. So we're trying to find d theta over dt. We do know just y, or we know when it's 30 meters above the ground. So we know y is equal to 30 at that point. But we also need theta. How do I get theta? So I have this is 30, I have this is 30. How do I solve for theta? Can you tell what theta would have to be? It would have to be 45. Do you guys see it? But you can always use that formula that we had originally, tangent of theta equals y over x. And you can plug in 30 over 30. So you say, when is tangent of theta equal to 1? And it's at 45 degrees. Or if you did radians, it'd be pi over 4.
How do you apply 30?
All right, so we end up getting theta is equal to 45 degrees. You can also do pi over 4, like I was saying. All right, stop. All right, take another round. All right, so when we plug in theta equals 45 degrees, or really theta equals pi over 4, it doesn't matter. When I take the secant of it, I get 1 over cosine, which would be 1 over the square root of 2 over 2. 1 over the square root of 2 over 2, which actually ends up being the square root of 2. You can work it out. It will work out to be square root of 2. And then squared. And then dy over dt, it was going up at a rate of what? What did I say, 3 meters per second? Okay, so we have 3. So when you divide out, you get 3 divided by 30 times square root of 2 times itself is 2. So divide by 60, right? Because this equals 2. So I get 1 over 20 d theta over dt is equal to d theta over dt. Now, question, what are my units?
Meters per second squared.
Okay, it's theta. So it's definitely per second something.
Meters per second squared.
What?
Meters per second.
Meters per second squared? Nope.
Radians per second.
It is radians per second. How did you know that, Lydia Schweitzer? You are a genius.
Well, because theta, in this case, you used radians, like root 2 squared.
Oh, but I could have used 45 degrees, right? I could have used 45 degrees, or I could have used pi over 4 radians. How do I make a choice?
We always use radians.
You always use radians every single time. Because radians is the non-unit. In calculus, it's like if all of your units cancel out, that's what you leave. And it, like I said, it doesn't matter what you put in here. If you have 45 degrees or something radians, when you take the secant of it, it's just a number. It's a ratio. Right? That's what our sine, cosine, tangent, all of those things are. They're trig ratios. So we get rid of all of our units. It's like just per second. That's all we have. So we say radians per second. So your answer is 1 over 20 radians per second. Okay, so the next one, so it says a construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of a plank. The worker pulls the rope at a rate of 15 meters per second. How fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? Do you guys understand this drawing? Can you see it? So he's pulling up on the rope, and this bottom is going in like that. And then this is going up. Yeah, it's kind of weird, isn't it? Okay, now what we have is we have a triangle. And I'll call this this length x. So we're going to have dx over dt. And we're going to have dy over dt. Now the dy over dt is increasing. Like, do you see that triangle that's created right here? The y value is getting bigger. So that's going to be the 0.15 meters per second. But the dx over dt doesn't equal the same thing. So we need to figure out what that is. We do know that the length of the plank is 5 meters. So that's a constant, so we can plug that in. So we have x squared plus y squared equals 5 squared. So when we take the derivative, we get 2x dx over dt plus 2y dy over dt equals 0. Normally that's where we would have a dz over dt, but it was 0. That's why it's all good to plug in the constant. And then we can divide out by 2 so they go away. All right, now we're ready to plug in. So we're going to plug in 0.15. But we don't have any of these other values. So what do we do? All right, stop. Okay, so it says when it's 2.5 meters from the building. So the x is actually 2.5 at that point in time. So we have 2.5, and then we still need to find y. So do you guys see, all we have is a right triangle, and we just solve it using the Pythagorean theorem. So you're going to do 5 squared minus 2.5 squared, and then take the square root. So we get 4.33013. So you can store that if you want. So store as A. I should have left more room. 4.33013. And then that allows you to solve for dx over dt. Okay, so I'm going to do times 0.15. I'm going to subtract that over. I'm going to divide by 2.5. So you get dx over dt is equal to negative 0.25981. So like negative 0.260. And then it's in meters per second. So